circle. You just move along 90, that's 20, 40, 50, 60, 70, 80, 90. So the pole to that plane, we call it number 1. Is here. All right, give me a second one.
323.69.
323. 363. And 69 again to the east.
Yeah.
All right, that's 69. And then 69, so that's 21, 31, 41, 50, 61, 71, 82. Okay, one more.
125.70.
25. 70, I assume, to the east again?
Yep.
Okay. So that's 20, 30, 40, 50, 60, 70, 80, 90. So the pole that is here is 3. Okay. So those 3 readings all intersect in that point, and that point is essentially 7068. It's the regional full vectors for that domain. So there's where they all intersect. If we want to find that orientation, I bring that to the east, west, and north, south. Doesn't matter. That's its trend out here. Its plunge is 10, 20, 30, 40, 50, 60, 68, and its trend is basically 73. So 073, 68 is the trend, and plunge of the F2 axis. All right. All right. So I plot the poles. Now the benefit of the poles is they're just points. They don't clutter up the map. So if you had a domain with 10 great circles and they didn't quite all intersect so perfectly, as is what would happen mostly in the field, because your measurements in the field are plus or minus 5 degrees. If you plot 10 of those, you'd have a whole bunch of intersections like this and that. You could tell roughly where it was, but it's just really messy and clutters up the stereo net. So it's much easier to plot the pole and interpret what the poles mean. So if I'm going to interpret what the poles mean, what should I do? What's the basic principle about how the poles relate to the following? Okay, and that they are more correctly, more specifically, they are. What is the importance of a pole?
It's a line.
It's a line, but it is. What is it about it? It's a line. What's special about it? All right, and there's one word missing out of that. That's close. It is the. No, there's a fishing. No, there's a qualifier. There's an adjective that's needed. It is the blank line that is perpendicular to the plane. It is the word is overused, but it's certainly appropriate in this case. Overused in the English language. You say, what is it? It is the. If the bedding is horizontal, what's the pole? Right. If the bedding is vertical, what's the pole? Horizontal. So I mean, every plane has a. This is nothing to do with geology. Every plane has a pole. Right. So what's the difference between the plane of this pole, the pole of this plane, and the pole of 90 degrees from each other. Well, how would you describe this pole?
It's the only one that exists on that plane.
The only one, it's the only orientation. Now you can actually draw millions of these things infinitely, infinite number of them in their location, but their orientation is, yeah, I would use an even stronger word. It's unique. It's the unique line. So, for example, if the plane is inclined, inclined plane. Together. All right. Forget about the ornamentation here. Here's an inclined plane. There's the pole, which is right here. So this plane, if the plane is horizontal, the pole is. If the plane is vertical, the pole is. Right? So in fact, if I told you the orientation of the pole, you'd easily find the orientation of the plane. So you can actually, they say it takes 2 lines to define a plane. That's true, absolutely true. The exception is that if you know the pole to the plane, you can define the plane. So the pole is the unique line. Well, all it takes is to define the plane. And in math courses, you call this maybe I'm taking math. The direction vector of the plane, or just normal to the plane. They use this if you're dealing with sort of vector geometry, it's called the direction vector of the plane, which is essentially the unique line that's at right angles to the plane. Okay, so what this basically means. Let's a couple of examples here. Here, the sides of this building are north-south. So now, let me just here. Okay. So the strike of this plane is north-south. Okay? The strike of the plane is north-south. What's the trend of this line? East-west. Plunging to the east. Right? So if I know the strike of a plane, if I rotate this around, what can you tell me about the relationship between the trend of the line and the strike of the plane? The trend of the line, which means I go look this way, and the strike of the plane, which is that way.
Oh,
Only 90 degrees. So the strike of a plane is let's say 120. The plunge of the pole to the plane is either, depending which way the plane is dipping, it's either the strike plane is 120. 30 or 210. It's one or the other. So it's got to be an angle of 90 degrees. So let's say the plane is dipping, is a strike of 120, and it dips 30 degrees to the south. Right? So that would be the southwest, right? So therefore, if that's the strike of the plane, what is going to be the orientation of the normal to the plane, or the pole to the plane? If it's dipping, if the plane is dipping to the southwest, then what?
210.
The plane is dipping to the southwest, so that's south. The plane is dipping to the southwest, so there's a 120 strike. The plane is dipping that way. Then what is going to be the trend of the direction of plunge of its pole? To the northeast. All right. So if that's the case, what's its trend then? Is it you're going to either add 30, you have to add 90 or subtract 90 from that? If it plunges to the northeast, it's going to be 90. So it's 030, and therefore what's its plunge? 60. It's got to be 60. All right. All right. Remember, if the plane is horizontal, the pole is vertical. So it's always a complementary relationship, right? So if the plane is horizontal, the pole is vertical. If the plane is vertical, the pole is horizontal. It's always a 90-degree difference. So if you want to do it this way, the way you can prove this to yourself is that first plane. Now let's say that. What was the orientation of that first plane, Alex? 008 that you read out?
70.
008, 70 to the
East.
So therefore, what's the orientation of the pole then? This is pole number 1. This is the line. So that line has that trend and this plunge. The plunge is 20 degrees. And the trend, well, you get it by bringing that up to north, right? What's that trend? 276, right? 76. So they say this was a strike at 8. Not quite, it was 276. If I plot it right, it might be 278 would be the exact answer. Right? So it's 90 degree. So it's a 90 degree difference in strike. The trend of the pole is a 90 degree difference, and the plunge of the line, if the plane is a dip of 70 degrees, the plunge of the pole is equal to 20. The plunge of the pole is equal to 20 degrees. Right? So there's a one-to-one relationship between them. If you know the orientation of the plane, you know the orientation of this pole. So therefore, what's the relationship of these poles in here? So we plotted 3 poles. Now, what you learn with Jamie is that if you now join these poles up on the same great circle, and what do? You plot these up in the same great circle, these poles are on the same great circle, then what? This is right out of one phase of folding.
Define your profile.
That's the profile plane of the fold, all right? So that's basically, if we, so where's the profile plane of this fold?
90 degrees.
Okay, so where is it exactly on this? Where on this diagram, this little model here, where's the profile plane? Profile plane's on a line, so you're going to show me a plane. Exactly, that's the profile plane. That's the cross-sectional plane of the fold. So what is that orientation of that relative to the fold axis? So what would you call the orientation of the fold axis relative to the profile plane? It is the? It is the? It's the pole to the profile plane. Right? So this is what the stereohead is showing you here, is that you take all these poles and you plot them on the plane. So what are we doing in here? It's translation between the reality here. So we have a fold. We're taking the poles to all these. So the poles are my fingers, basically. Each of my fingers are separate poles. So here's our fold. That finger there is the pole to that plane. This finger is the pole to this plane. This finger is a pole to that plane. Okay? All those poles lie on this front plane, the cross-sectional plane of the fold. So we call that a profile plane. It's also just a plane in which is the cross-section. And if you're in the field and you look at a fold, you were taught in field school to look down the barrel of the fold axis. Why? If you look that way, you get a distorted view. To get an undistorted view, you look down the fold axis, down the barrel of it. That means if you're looking that way, the plane you see is this. So if you're looking that way, the plane you see is the plane of the board. So your line of sight, you have the best view of line of sight because your line of sight is at right angles to the board. So your line of sight is that, which means your best view is this way. Okay? So your line of sight is down the barrel of the fold axis, which means you're looking at the proper orientation, the cross-section of the fold. So this is known as the profile of the fold, or the profile plane of the fold. It's the cross-sectional view of the fold. And it's the section of the fold where you see the angular shapes in the true perspective. So if you view my fingers to be all the different poles, like that, then each of those poles lies on the profile plane. But what's the profile plane? It's a great circle. So therefore all these poles lie on the same great circle. So the pole to this plane, my fingers, my hand is a plane. All these fingers are different lines on that plane. The pole to that plane is this line. Okay? So if you plot all the poles to the planes instead of the planes themselves, you end up just with a plot with a bunch of points on it. You draw up in one great circle, you plot the pole to that, and that's the fold axis. And lo and behold then, you'd have a whole bunch of readings that you would have made in this domain as well, which would back that up. So, by far the best way to analyze these things is to use the planes, because if the bending readings are slightly off, then what you're going to have is a whole bunch of intersections in here, somewhere loosely grouped around there, but there's not a very precise way of defining where they intersect. But if the poles are just slightly off, you can still put a pretty good best fit great circle through it and define more precisely what the hinge line is, the full axis of the pole. Okay. Well, that's good because we're going to some general points as well, not just specific points. Okay. So what do you want to move on to now? That one? Okay. What time is it now?
It's 6:16. If we could do the last lab, I think it'd be better than the second one, just because that one's a lot harder, and I'd rather make sure we get that one.
Okay.
I don't even have the last one here.
Which one is the last one?
There's part of one. We don't have to, I just I would like to make sure.
Oh, sure. Okay, that's fine.
I still don't have any questions for that.
Oh, that one, yeah. Okay.
I don't have a lot done for it though. Yeah, so apparently.
Okay, so we can go through that one. So what? Again, the trick is to divide the thing up into domains. So find something that's constant in a given region. And your hinge surface traces help. So why don't you give me what you've...
Okay, I have a minor fold X.
Let's look at the map first. You got the map there? What about the hinge surface traces? You can't really get going on this until you plot the hinge surface traces. So, talk me through the hinge surface traces on this.
So you have one giant one running through the middle of.
Have you got your map there? So why don't you come up and do it on the... You do it up on the projector here. It's easier, isn't it? Alright. I mean, what I would just say to that, yes, you just have to define them as precisely as possible, because that would be going through a limb. You're going to go through it as on a curvature. So, yeah, so you take it through that. Everyone see that? Have you on the way to that?
No.
Anyone on a razor?
Oh, yeah.
Okay. Really important. It's really important to take the time to position these right, because if you're going to go through, you can't take the hinge surface trace through here because that's planar on both sides. You've got to take it through a zone of curvature, so you've got to take it like that, and then you've got to bisect those there. And the reason for doing that is you've got the same, it's a mirror image on either side here.
Yeah.
Okay. So that's certainly one hinge surface trace line. How about the other, or another?
Could you go, like here, these ones?
Yeah, absolutely. As long as you see, the reason why that's a hinge surface trace is because you've got repetition on either side. Now, this is when you put a hinge surface trace in, you ask yourself, is this a local mirror plane?
Mm-hmm.
And the answer is yes. You've got the same things on either side. You've got a purple unit going around here like that.
So could you make one the whole purple unit then? Yeah, like
Goes
throughout.
all the way through around.
Well, no, because if you were told that there was only one of this yellow unit, if I said to you, or you found out that this quartzite was the same stratigraphic unit as that, so there was the same layer to deposit to start with, then yes, you would have to do that. But if it's just an independent sequence, then the several original layers of whatever this is it quartzite or whatever, what's that? Yeah, quartzite, whatever it is, then if it's just an embedded sequence, then the answer is no. Okay. What else? So basically, have you accounted for all the curvatures?
Is there the one on the right there?
What about this one here? What about that one?
Yeah, so you go like through here.
Yeah. Not only can you. No, I would. Should is a sort of subjunctive. You must. The imperative. Okay. Not only can you must. And again, it's going to go through the zone of curvature in there, so it should be right there. Okay. So, like hinge surface traces, you've got to take the time to your dribble marks away if you put them in too quickly. Okay. So, I guarantee you, if this was your job, the person who's looking at your map, their eye is drawn to these hinge surface traces. Okay. So, what areas of the map then are the ones to avoid? Because
Crossing.
where they cross is where that will be a disaster. So those areas are disasters to start with. Okay. So what you really want to do then is plot up. This is a clear candidate domain right here, and this is a candidate domain here. Okay. All right. So what you need to do is plot up something from the northern domain. Now this is similar in strategy to what we did in the other map. We went away from where those folds interfere with one another. Okay, so have we got the data of that domain?
So the dots are the poles.
All right, so here we have a little bit of a problem here, and that is that
And is this in the top domain? Yeah.
yeah, so we're confronted with the problem here that anticipated from the previous one, and that is, this is more realistic. Is that the great circles, they look like they're converging on intersection down in here, but they're not perfect readings, and so there's a bit of wobble in them. So this would be a lot better and more precise if instead of these being plotted, the poles are plotted.
Yeah, that's because it's this one.
Sorry? Okay.
That one.
So these are the poles here.
Yeah.
Yeah, okay. All right. And so you plotted the great circles as well?
Yeah.
That's fine. There's no poles plotted. Okay. Okay, so what are we interpreting here? Remember, you're interpreting this map as if, or this domain, as if the rest of the map didn't exist. So what do you see here? represent each of these great circles? They are? Well, the legend will tell you what they are.
Oh, they're bedding.
Right, so the bedding. So the bedding, these bedding great circles, they all converge on this, and these are the poles to them. So what should I do with these poles?
Draw a great circle for the poles.
All right, so if I do that, find lo and behold, you rotate them around. Look at this. Right? So they plot on a pretty tightly confined great circle in that domain. So it's not perfect, but anyway, the best great circle like this. Sorry, Andy, I'm giving you some annotations here. So what's that? So what do I do now? If that's the best fit great circle. These are the poles to the planes. So you know from the map you're going across a pole, right? You don't diverse the stereonet from the map. The map, you know you're going across a fold. You've gone across a fold hinge. So what's going on here?
So that creates your profile plane thing?
That's the profile plane of the fold in that
And the bedding.
fold in the bedding in that northernmost domain. And it's absolutely no different in principle than the previous map. It's a bunch of bedding planes intersecting in a common line. It's translated on the stereonet means a bunch of great circles intersecting in a common point. Okay? Maybe this great circle I'm using is slightly different diameter than yours, but okay. So what do I do? I plot if this is the profile plane, what I would do is,
Plot the poles that have them.
and it comes out in here. So I just count 90 degrees from here. So it's in the plotting position for the pole now. 10, 20, 30, 40, 50. Looks like 55, 55. So that is 35 to here. 3, 4, 55 is right in here. So the pole to this plane is right there. Okay. So that is exactly this relationship. So if you're plotting great circles, you plot a whole bunch of great circles around the fold, they all intersect, they all contain, remember the reason why when those great circles, you plot all these planes around the fold, why they intersect in the fold axis is because that's how the fold is generated, by flexing around the axis. And so all the possible orientations of bedding around the fold all contain this line. Or geometrically, as Jamie would have said to you, I can generate this surface not mechanically, but geometrically, by moving a line parallel to the southern space. Look at this. All I'm doing, I'm not going to change the orientation of this line. All I'm going to do is change its position. And as I change its position, I've traced out that fold. Right? I've just traced out that fold. I could slide this line all the way along that surface. My hand's getting in the way, like that. Right? Which basically means, therefore, that all bedding planes around the fold must contain this line. They have to. And so where they intersect, that means they define that line. Okay? So that's the great circle. That's why all of these great circles all intersect in that fold axis. Then, why the other geometric relation works, if I now say I'm going to plot the poles of my fingers, they all lie on this plane, the profile plane or the cross-sectional plane, and the pole to my hand is pole axis. So we go, if you want to go to this route and plot the poles, take the pole to that plane, you end up with the pole axis too. So you've got two ways of doing it. You plot all the great circles and see where they intersect, or you plot the poles to those great circles, line that up on one great circle, find the pole to that, and that gives you the pole axis too. But crucial thing is, this is no different than the other map. Same geometry. Okay, now is there any other fabric in the north that you could have plotted there? You've given me bedding readings. Is there any, what about the other fabrics on that?
Yeah, you can plot line of pole axes.
And where do they plot? Give me,
A lot of the poles.
yeah, but that's for the whole map.
Yeah, the north would.
remember, when you're defining a domain, the rest of the map doesn't exist. So that composite
So
plot is very good for when you're putting the blocks together. Okay. Where's the note here? So where would you describe them relative to this stereo net?
right, where the full axis is.
Yes, exactly. So the local fold axes that you've got in that domain as you go across the fold, right here. The plot right there. So that's identical to what you had in the previous map. Same geometry. You don't have the second fold phase to complicate it. I think it's even simpler than that. Is that you've got, yet again, you've got a whole bunch of great circles intersecting in the common line, or you've got a whole bunch of poles, the line, one great circle, and the pole to that is that same common line. And then not only that, you've got data within that same domain from minor fold axis to the open line here. So all that is no different than the previous map. Okay. And if you do that in successive domains, you'll find the same relationships. So the trick then is to start putting them together. So your plot there, that you just were about to show me, so you put all the fold axes together, is the next step. Is you do that in several domains. Then you ask yourself, well, I've got to start putting this together. And this is a composite, and it's like the size of my stereo net, different from the size of yours. That's okay, but you still get the general trend out of it. Is that these are all coplanar. So all those minor fold axes throughout the entire region are one plot. The ones that come from the northernmost domain plot down here. But if you put them from different domains, they all are collinear. And again, that is no different than the previous map, where you plotted them all together and they all came out in the same great circle. Okay? No different. So, then, are these, so what are the possible interpretations?